The broadcast is now starting. All attendees are in listen-only mode.
Okay, we'll get started. Oops, I'll just share my slides. So, thank you everybody for joining. My name is Eoin O'Flanagan. I'm a data engineer at NewDay, and for some reason my screen share is playing up. Sorry about that. I'm a data engineer at NewDay, and for the past 18 months or so, I've been working on our migration from our on-premise data center to a PCI DSS-compliant cloud-based platform, cloud-based data lake. So what I'm going to do today is just talk you through some of the principles we followed, some of the ways we've built our applications, and what the technologies are we using. And the key takeaway really is about, if we're to do it all again, what we may do differently with what we know now. So just to tell you a bit about NewDay. NewDay are a credit card issuer, been around for about 20 years. We have approximately 6 million customers, all in the UK. And we have our own range of our own credit card products, and we also have co-branded products with people like Amazon and Debenhams. For the past 18 months or so, we've been undergoing a major digital transformation program. And you can see it touches across several areas from, updating our digital customer-facing applications, improving our engineering. But the key one for us is around advanced data analytics, and that's what this project has really come from. So just to talk about NewDay's existing technology landscape, you can see at the top we have a range of users from quite technical data scientists through to people in marketing who just want to do customer segmentation, through to finance analysts and risk modelers. So the current infrastructure, the way they get served the data, it's a bit of a mixed bag. Excel is a primary query language. SAS is then used for a lot of the modeling, and then we actually have this mix of data databases. Oracle used for our co-brand solutions, and then Microsoft SQL Server for our own brand. SFTP is king, so batch file-based transfers are king, and that's how data gets transferred in and out of the environment. So pretty slow, pretty batch-oriented, not really great. So we need to solve some challenges here. Definitely scalability and performance is a big one. It's very hard to extend. It's expensive to extend, as you're probably aware, with an on-premise environment. We can't really do any level of data segregation, and that means that if you get access to the most sensitive data, or to the data, you get access to the most sensitive data. So we can't really say user A can see customer names and user B can't. Well, once you get in, you see pretty much everything. As you can see from the technology choices, it's very difficult to do data science and apply sort of more modern day algorithms and modern day approaches. And we do have some real-time use cases, but with this stack, we can't do streaming. It's all about batch processing. So the solution is what we've called Nexus. It's our Nexus data platform, and it lives on AWS. And the key thing this is trying to do, we want to support modeled and unmodeled data. I think every data lake does. We want to give our users much more self-service capability for both reporting and data preparation. We want to also, we have very, very wide and very quite difficult to manage data sets, and we want to really help our users do much more around that EDA, that exploratory data analysis use case. And lastly, the key one for us is, building for data science and the modern Python, Scalas, Sparks, the things that are kind of the up and comers in the data space. Technically, we have achieved PCI compliance. We're PCI DSS compliant for a portion of the platform, which I'll explain later. But beyond PCI compliance, so for those of you that aren't aware, actually, PCI compliance means we can process a credit card number. We are able to handle credit card numbers securely, and we are tested for doing that. But beyond that, we also do more data sensitivity segregation. So if you are if you PII use cases, personally identifiable use cases, we do even segregate down to there. So we do treat data much better than the existing platform. We're metadata driven, and I'll explain a little bit about how that works later on. We support both stream and batch use cases, and of course, we can do proportionate cost and chargeback, so we can cross-charge within our business for users of our platform. The guiding architectural principles we've tried to follow, key one for us is about building this many self-contained systems over one big monolithic thing, and I'll show you how we've broken it down later on. When it comes to technology choices, we've chosen open source first. If we can't do open source or it doesn't feel right for the use case, we try and do something that has open source APIs. And at the very last, we'll utilize proprietary software, and we've tried to avoid proprietary software as much as possible in the stack. Again, our choice of what we deploy to, if we can deploy it to serverless, be that function as a service, so like AWS Lambda, or database as a service, like Amazon RDS, we'll do that. And then we also deploy a lot to container as a service, but and avoid IaaS as a key principle. So just to actually show our platform, any data platform needs to get data from its sources. So we have these three key sources: our customer transactions, we have digital APIs, and we have our payment processor, which actually comes from a mainframe, is our payment processor. And we need to get that data through to the consumers of that data. We've broken our system up into 5 key pillars. So we have an ingestion layer, a streaming layer, a data lake, presentation layer, and then our end user tooling. Now, the reality, as you know, it would be nice if the data just flew from left to right, but the reality is it's a bit more complicated than that. Obviously, to support all those layers, we have infrastructure services that sit across that, such as all our DevOps and security and everything like that. But we're really going to drill in on these top 5 components of our architecture. So just to talk about ingestion, what is our ingestion layer doing? How do we utilize, or what does it try to do? The key things we want to try and do. So we get data sets in from our third parties, our payment processors, or our people we might buy source data from for various use cases. And initially, our key goal here was to make all these data sets available immediately for query. So that means making these, obviously, some of them are quite complex data sets, human readable. We get about 100 gig a day, and that is across multiple sources. So we get CSV, we get XML, we get acidic. For those of you that aren't familiar, acidic is a format that comes from some mainframes, and it can be quite complex to read. And we get a variety of file sizes, so we have to support both tiny, pretty small files all the way up to 30 gig, and I think we even get more than 30 gig files every day. The key component of this platform, or this layer, is that we protect our personal account numbers. So we protect our PANs at ingestion. And the way we do that is via a tokenization. So the technology we use for our ingestion layer is actually Akka. We use Scala. We haven't used any off the shelf. This is something we built from the ground up. And this is really because we have to support this wide range of file formats. So at the top layer, if you imagine the data flows from top to bottom, we decode the data, we understand if it's acidic, we understand if it's ASCII, whatever data type we get in. And then the first thing we do to that data is we parse it to Avro. So Avro gives us the ability, it basically gives us a gateway. We can pass the data through, and we immediately know that field 1 of row 1 of this table, we're expecting a string, and yes, we get a string. Field 2, we get an int. So immediately we know if there's something wrong with our data on that first pass. Once it's in Avro, once all our data is in Avro, we try and tokenize it, and we actually I'll talk a bit about how the tokenization works later on, but we create a non-reversible token. So that means that every credit card, as soon as it's passed through this, it's no longer an actual credit card number, it's a token. So our end users aren't directly working on credit card numbers, I should say. And then beyond the tokenization, we have this idea of data segregation. So we have this data filter component, and that's where we might say, for this PII field, for this name, we want to send one copy to our PII zone and null it out, and send another copy, or send one copy to our non-PII zone and have that nulled out, and send a second copy to our PII zone, and it's not nulled out. And that gives us a nice segregation at read. So we define that all in Avro schema, and we can decide where to send specific fields based on data sensitivity. We have the options here to do 2 things. If we need to produce our data to a stream, we have a Kafka producer. For most use cases right now, we're actually writing this straight out to S3. So we produce an Avro file or a Parquet file on S3. which can then be picked up by our downstream systems. The way we actually deploy this is Docker. Docker is king for many of our use cases, and this is a single Scala Akka application that's deployed in Docker, which we then deploy onto Amazon ECS. And Docker is fantastic for, as you're probably aware, building locally and deploying to a remote system. So just in terms of how that fits into the bigger picture within AWS, if you imagine, if you look there, we have a file that contains customer data. It's an acidic file. And we get our feeds, they all land on S3, and we use SNS, we use S3 notifications. So as soon as the file lands on S3, this Lambda system at the top tries to pick that file up and parse it, and that Lambda system uses some metadata that we define in a schema to try and understand what is in that file, and based on what's in that file, based on its name, it can try and apply a schema to it. That Lambda then also, given it knows what file it is, spins up an ECS system, which actually spins up our Akka system in Docker containers. So this is fully event-driven. It's fully ephemeral. So as soon as everything's spun up and processed, it all shuts down afterwards. That data then gets landed out to S3 or Kafka, as you see. So as we said, yeah, it's entirely event-driven, and again, we can do file-specific cost appropriation. So if we get a specific file, we know how much it's going to cost to process that file because all the infrastructure is spun up to just process that file. Equally, we have configuration-based throughput, so that means we can control how quickly we ingest this file, and obviously, by how quickly, it means we can actually play catch-up. Say we have a file that takes an hour to normally process and tokenize. And that's fine. We're happy with that hour, but we miss SLA for whatever reason for one day. We can dial this whole system up to process that same file in 5 minutes. Obviously, it will cost more. We use more AWS resources, but it's completely configurable how fast we can process and tokenize a file. The PAN tokenization is reversible because we utilize DynamoDB. And just a quick example of the way we do that. So here's an example of a credit card number. It's not a real one, unfortunately. But we take that credit card number and we store it in Dynamo, and then we create this token. So we keep the first 6 and last 4. That's quite useful for analytics. But then we actually generate a random string that gets put into that token. The token is what persisted down into the lake. And if we ever do need to go and re-look up a PAN, we will have to come back to this DynamoDB token store to figure out what that PAN number is. Doing this all again, I mean, this is a pretty successful part of our system. We utilize AWS step functions to manage our Lambda system, and they are absolutely brilliant. I would highly recommend them. Equally, DynamoDB, if you're not familiar, it provides extremely fast read-write, and this is one of the key things that lets us process this data so quickly, is using Dynamo. When we originally started this project, Lambdas had a limitation of 5 minutes uptime, so we couldn't really utilize them to process data in any real quantity. That's now improved, and if we're doing it again, we might probably consider using Lambdas over Akka actors, but still our Akka system works pretty well, so we're not going to look to replace it anytime soon. Now just to quickly touch on our streaming stack. So for streaming, obviously, if you're familiar with Kafka, you know, it lets you provide a single interface for streaming for ingress and egress. And one of the nice features Kafka gives you is Kafka Streams. So you can perform, sorry, apologies for this. One of the nice interfaces Kafka gives you, or one of the nice tool sets Kafka gives you is Kafka Streams to perform ETL on streaming data. So the way we use Kafka, we actually have a feed from our, apologies, I don't know why my computer keeps doing that. So we get a feed from our apps, our digital team, who provide real-time data in JSON. And similarly, we apply the same kind of logic. So we have our data filter concept. So we identify using an average schema what's a PII field, and then we can choose to send that to a PII zone or a non-PII zone, depending on the use case. Equally, we can ensure our data is secure by having an app that literally scans every record coming into into Kafka and checks it for pan. So we can check. So there's a thing called a LUN algorithm, and that's a way of checking if a 16 digit string looks like a pan or not. So we can actually raise alerts if something is coming in that is highly secure data. It's all in flight, it's all real time, and then we've utilized Kafka Connect to land data out to S3 as Parquet format. So one of the other things that this infrastructure provides is actually Kafka and the schema registry provides our central store for Avro schemas. So every step in our pipeline utilizes Avro schemas for definition of the data it's looking at, and we use the REST API of schema registry to constantly refer back to those Avro schemas centrally, so they're all held in one place. Kafka is deployed on ECS at the moment, so it's all in containers, Elastic Container Services. We will probably, in the future, look to deploy that actually onto Kubernetes as we want to grow our Kafka cluster. It's a fairly small Kafka cluster at the moment, so if we wanted to make it bigger, we would probably look to move it over to Kubernetes. What's great about Kafka, I don't know if you're familiar, but Kafka provides something called exactly once. It's a concern with streaming so that you can get duplicate records. Exactly once guarantees that you process each record you land onto your streaming environment only once. And we thought when we deployed it, there would be a processing hit because for every message sent, there has to be an acknowledgement that this, the receiver has received that message and has processed it. Actually, we barely saw any hit, we barely saw any overhead, so it was absolutely brilliant. We did think we could write our own version of Kafka Connect better than Kafka could, so we originally utilized Kafka Streams, and we tried to write our own version of the Kafka Connect connectors, and that's because we wanted to implement a fairly complex partitioning scheme. We then realized, through a fair bit of pain, that we could implement that custom partitioning within Kafka Connect, and the benefits you get with Kafka Connect for landing to a non-Kafka source is well worth it. It works really well. We didn't buy Confluent, so we didn't buy the Kafka Enterprise, and so it didn't come with that nice Confluent Control Center feature that you get when you buy Kafka from Confluent. So we do still struggle even now with the logging and instrumentation around Kafka Streams. It's very hard to get to, and if you do lose a record somewhere in this process, it can be very hard to trace down where that is. So that's something we are going to look at in the future. So just to talk about the lake component of this, obviously a lake, what does a lake do, a data lake? Well, it wants to persist a history of all our ingested data and our derived data. We want to make our metadata centralized and searchable. And obviously, we want to apply the ETL to our data, so the transform, verify, publish, QA, all of that good stuff that you want to do in an ETL pipeline process. The way we're doing it, this is probably the most standard architecture of our platform. We utilize Spark for our ETL, and we actually utilize AWS's data pipeline, which orchestrates Elastic MapReduce clusters. So it spins up the cluster, it then executes the jobs on that cluster for you, and then once the jobs are finished or they failed, it shuts that cluster down. We utilize AWS Glue for those of you that are, well, specifically Glue Data Catalog. So those of you familiar, it's like a Hive metastore, but it sits across your data in S3, and that is absolutely fantastic as a nice way of cataloging all the files you have on S3. You can treat it like a SQL database, so Spark can literally read from that and say select star from table 1, and then Glue does the work of figuring out giving you where on S3 table 1 is stored in terms of the files. We've written our own way of triggering our pipelines, so we wanted to make it quite event driven. So again, we utilize Lambdas, similar model to our ingestion. And that's what triggers our pipelines at the right time when the right files are in place. And there's a whole kind of QA process that sits between that verifies we have the right row counts and the right expected files in place to trigger the right pipeline. You can see again the file metadata, the Avro schema is key, and that's where we actually define our transforms in the Avro schema for a lot of our jobs. So if you want to convert a string to an int, we will just mark a field in that schema as convert this string to an int, and then Spark picks up the work and applies it. One of the cool things is, yeah, we use S3 as a source of truth, and you'll see that further down our stack, S3 continues to be the source of truth for the whole stack. We do have this nice schema-driven ETL, which works really well for most use cases. We've had to break the idea of using schema-driven ETL or config-driven ETL for more complex tables. But I think for 80% of our use cases, we can do this schema-driven ETL approach. Blue Data Catalog works really well, and we actually, for our business definitions, we store those in Calibra. So a user who wants to look at what field A contains, they can go and log into Calibra and take a look. Looking at this all again, originally we started out with Avro files. As you see, Avro was kind of key to our platform, and we had large Avro files, small Avro files, small Parquet files, and definitely we've settled on large Parquet files, which I think is kind of understood in the industry. There are behind the scenes, we've actually started to implement compactor apps, which will come along, and if where we have a directory of small files for whatever reason, be it it's come out of streaming, or it's a particular use case has forced us to have to write lots of small files, we have a compactor that comes in and will compact those up to larger Avro files for performance. There was an option to use ETL, Glue for ETL. I don't know if you're familiar with Glue for ETL, but it provides a serverless Spark environment. What's really cool about that is you don't have to spin up EMR clusters, you don't have to worry about EMR clusters, but the developer experience is pretty horrible at the moment. You're kind of stuck developing in the browser, so you don't have the nice IDE experience you get when you're just writing raw Spark. So we discounted that early because of that developer experience. You couldn't write unit tests, you couldn't develop locally against it. Everything went into one big monolith ETL app early, and now we've started to break them down into ETL micro apps with a common library. And that's really for a maintenance thing. It sort of made sense to have one ETL app with, the schemas driving everything, but it made our different, creating a dimension or creating a fact table or creating a slowly changing fact a bit more fiddly when it was all in one place, and extending that was hard. Lastly, data pipeline orchestration is okay. We are probably going to move off data pipeline orchestration for spinning up EMR clusters and look at something like Apache Airflow. We definitely find there's limitations around restartability. There's limitations around how many jobs you can run in parallel on a Spark cluster or on an EMR cluster. And it's one area we kind of hope Amazon will look to improve, because right now we don't think it's great. So just talk about how we're presenting the data to the users. So key, we want to provide query optimized data sets. So we want to make sure that we're not optimizing our data for our pipeline, we're optimizing our data for how our users consume them. We want to make sure that the right users see the right data sets. And also we want to we have to publish to several targets. And actually we published to one target, which is S3, but then we have things that read from S3 further downstream. So just to talk about that data segregation thing a bit, you can see at the top, we actually utilize, or you can see we utilize different AWS accounts for different data sensitivities. So all our PCI data actually persists in its own PCI account. That's where our ingestion process runs, and that's where our token store, that PAN token you saw at the beginning, persists. What's really nice about this architecture is you can really heavily lock down that one account and be very, very, very confident, and that is a super secure area that it is fundamentally difficult to get access to, and you need to have a much higher level of privilege to get into. Our ingestion process then spits the data out into our non-PCI account, and then within that we have logically separated AWS buckets for our PII assets, so our personally identifiable information, and our non-personally identifiable information. That all persists in those S3 buckets, and then we are hosting or providing an enterprise data warehouse, a SQL warehouse, over the top of those buckets for our users to query. By default, a user will get into the non-PII, and then ideally they would have to escalate their privilege for a temporary project or a temporary use case to get access to PII data. And that's really how we're trying to limit our exposure on our risk on who can access what data. By default, you get an anonymized data set. Obviously, it's still commercially sensitive, but it's anonymized. So if something, there was a breach, it would be very hard, or wouldn't be as potentially as bad as if some PCI data got out. So just our tooling. How are we getting our users access and able to run queries? So we want to offer the latest and greatest in terms of the technology, and we want to be able to provide a platform that can continue to offer the latest and greatest in terms of technology. We obviously want to have the right audit and security around the data, and we have to support this broad range of users. And part of this project has actually involved migrating our users from SAS to Python, which has definitely been an interesting journey on that front. So if you think to the way we host our data's on S3. We have our SQL layer in the middle, which is directly querying files on S3. What we've actually done initially is we've provided our users a browser-based environment to access the data. And the first tool we've deployed is Superset. Superset is an Apache project. It's developed by Airbnb, and it provides a SQL IDE. It does do visualizations as well, but it provides a SQL IDE over a database. And that's been quite nice as an initial, we need to get this stuff out to users quickly. It's not brilliant, and we'll talk a bit more about that, but it definitely works to get users doing that exploratory data stuff on the data we're providing. For our more advanced users, we've actually built a Jupyter Hub environment in Kubernetes as well. And this is quite cool in that each user logs in, they hit this Jupyter Hub spawner, and then it spins up their own. Each user gets their own containerized environment with their own constrained resource and the right libraries installed that they need to use. What's really cool about this is we can configure the resources based on the user needs. So certain users can have a higher memory instance. Other users might just have a simpler instance because they're just using Python to execute SQL against the database. Lastly, we enable our users to schedule jobs. So we don't just schedule jobs, and we have a nice Airflow system that works in Kubernetes as well. A user can actually pick up a piece of code that they've written in Jupyter and easily run it in Airflow as a batch job that runs daily, weekly, monthly, whatever they need. We actually use the same container image for both Jupyter and our Airflow environment, which means a piece of code that works in Jupyter will work exactly the same in Airflow, so they can schedule their jobs, and that's working really well for us. The way we're keeping this secure, and as you're probably aware, AWS and security and AD, Active Directory don't play that well together. So we're actually providing an Active Directory layer in the browser. So as a user logs into one of these tools, they are authenticated against Active Directory, and then that Active Directory authentication is mapped down to an AWS IAM role, which has some limitations, but it's been a really kind of nice approach for us to get people started on utilizing this environment. We are going to take it to another step further, as I'll describe in a minute. So what's nice about this environment? Well, based on an AD group, we can configure the resources to a user or to a specific user need. It's so flexible. Equally, it's very easy to extend. Being in Kubernetes, it's easy to provide more pods or provide more hosts to run pods on. So scalability and extensibility is easy. And then because we're using Docker images, it's very easy for us to make offline changes and deploy them to users without impacting. We don't need to do much in terms of downtime to provide new upgrades to the environment. Equally, our users have, we can customize it very specifically to very specific needs. So our scientists who might want to have more advanced environment, they can get that without us having to maintain so many different use cases concurrently. Obviously, one of the negatives is you do get for what you pay for. Superset's free, it's great, but for some of our less technically aware users, it's been difficult for them to use, and I'll talk about how we're solving that in a moment. Equally, doing that security and flexibility and usability thing, it's never that easy. So we needed to, we went through quite a lot of pain providing that, and it's how we ended up with this model, which kind of works. Our users still want to use Excel, and without being in a Microsoft SQL Server stack, to get the performant Excel over this environment is very difficult, and we have a solution upcoming on how we're going to do that. So just some key takeaways. No, I'm very short on time, but some key takeaways. There's talk about using Lambda and Kappa architecture. People say that the Lambda architecture is dead. We don't think it is. Batch your batches, stream your streams. Don't try and force a batch to a stream or a stream to a batch too much. It can get painful. Always design for change. The rate of change, especially in environments in AWS or Azure, as new features are coming out constantly. And we've seen even some of our pain points and ways we've put workarounds in to try and solve. AWS have solved them as well in concurrently. So always design for change, design in a modular way, because you will be wrong eventually. Not it's just happening much more quickly now. We definitely think to build orthogonally, so build horizontally. Don't try and build one component of your environment and get it perfect. Get the data to users, get the technical features to users, get that feedback loop built in. Otherwise, you could find yourself having to go and retroactively do a lot of the hard work again. Get your data up to AWS or your cloud provider using their bulk load system. We utilized AWS Snowball. You can see it there. Plugs it into your network and load all the data up and send it. Getting loads and loads of data up over the network would have taken ages, and so Snowball is a fantastic service to get your data over to the cloud. Lastly, try and centralize your data access management into one place. We used AD. It was painful, but it's paying off now. Trying to maintain multiple ways of having your data or multiple ways of authenticating the data will be difficult. So definitely keep that in mind. And also, lastly, well, just to mention, I'll be taking some questions. So if you want to fire some questions in now, I will try to answer them at the end of this. So please fire away. But while we're doing that, just to talk about where we're going next. So we are looking to unify our data preparation and access. So we're building a centralized data as a service layer that is going to be in a technology called Dremio. When I did this slide, we hadn't bought it, but it's worth looking up. It's Arrow-based, Apache Arrow-based, so very, very, very efficient in-memory data processing. And what that gives us is a kind of a centralized data as a service layer for more clients and more tooling. So we can support the browser-based clients, but we can also extend out to our desktop-based Microsoft Excel and Tableau and get much more performance out of them. And equally, one thing it will give us is an even wider range of tooling. So this is where we're going now. This is our next step in the journey, as it were. It's all about, we have a nice way of getting users from getting data from A to B, and now it's about solving it for even more of our user use cases and giving them the most flexible environment possible. And that's it. So thank you very much for your time, and if I will be taking questions now. So if you want to put them in via the chat box, I will spend some time answering them. Thank you very much. So I think we're going to get some questions through now. So one of the questions we have is, how did we combat the skills gap? It's a very good one. I think one of the key things we did is, if we just look at this architecture here, is we had to enable an environment where we could support SQL and get SQL users on early. And then a lot of the work we did in Python was about writing user functions that kind of took away some of the pain for a less technical user to be able to query the database. So we did the work for them. They just import a common data access library, and we did the work of connecting you to the database, connecting you to Sandbox, writing easy functions for them to read data in and out. So that meant they just needed to focus on the actual data munging or data modeling work they wanted to do, without having to worry about learning about where does my data live, what is my data stored at, is it Parquet, is it a database, so on and so forth. So that's the way we try to combat that. We've done lots of training sessions, obviously, and one of the key things is responding to user feedback as we go and develop in a much more agile way. We had another question about what our backup strategy is. I think if I just go back to a previous slide, so the idea of everything in S3 is the source of our truth. So we keep all our data in S3. We have that glaciated off, the usual kind of S3 backups. The way we've done, we then back up our Docker containers as well onto S3. So everything is backed up onto S3, and because we're completely ephemeral, we know we can kind of spin up an environment elsewhere pretty easily. We haven't really had to worry too much about snapshotting or anything too painful there, because we have everything backed up as containers or as code. So that's the way we're handling backups at the moment. So the next question we had, support for R. Support for R is actually coming. That's a very good question, and that is why we built this environment here. So we're using Jupyter. Jupyter notebooks give you the ability to have custom kernels, and we do have on our backlog to provide an R kernel for our users, and it should again be very easy to extend. We actually have a Scala Spark one now that I'm working on, but yeah, R is there, or we are able to support it right now. Next question we had, is our Active Directory Microsoft or Open LDAP? It is all Microsoft. So NewDay, as you probably saw in the beginning slide, was very much a Microsoft house, so yeah, we've kind of stuck to Microsoft for our Active Directory. So we've been asked what was our team size and project iteration to deliver this. It's probably taken us about 18 months. And our team size was probably about 30. We had a good amount of devs, upwards of about 15 devs, I think, and then there was a suite of designers, business analysts, project managers, and obviously ops people, DevOps resources to do it. So it has been a fairly big project to deliver over the past 18 months or so. So we've been asked, can we use this to deploy models in production? Yes. So if you have utilize Airflow, so you build your model in Jupyter, if you have basically a Python app, you can pick up that model, that scoring or whatever that model is, train it in Jupyter, train it in the Jupyter environment, and then run your scoring on Airflow in a production way. We have teams already building that now. Longer term, for maybe more complex model use cases, or if you want to do sort of model monitoring or check how a model performs over time, we're probably going to look at utilizing something like AWS SageMaker, so that's the way we've been working through. Well, that's the way we're probably going to go with model deployment. Someone just said, my Amazon Platinum card, NewDay portal is the best credit card on import ever used. Thank you very much. I wasn't involved in that, but good feedback. Thank you. Any other questions anybody wants to ask? We've still got 20 minutes or so. What do I think would be the lead time to onboard a new client onto this platform from an end-to-end solutionization perspective? So I think it really depends. We've actually written this to be as generic as possible. I think if you were going to go, if I was going to start this all again, I mean, I've tried to sort of give ideas around things to look at in terms of if you were to build this for a new client. I think you would be looking at a 12-month lead time, depending on the volume of data. It really depends on the data and what you want to present. We have to present 100 tables, more than 100 tables to our end users, which, as you can imagine, is quite complicated. But the thing is now, I mean, when we started, AWS didn't have, they now have a cloud formation platform called AWS Data Lake, which actually does a lot of this work for you. It does a lot of the spinning up and sort of creation of the VPCs and the network side of things, and deploying Glue and S3 and everything else. So if I were to start this all again, I would definitely utilize that. Unfortunately, when we started, they didn't have that nice template in place, so we had to do a lot of the work from the ground up. But I think, depending on the volume of data, for me, it was it'd be a 12-month thing for a client equally sized to NewDay, maybe longer. Packaging management is a question. So we utilize Artifactory for storing our own packages. For Scala, I guess you're asking around how we deploy our own packages. So we put everything into Artifactory, and we have our own Maven repo, or we have Docker repo, or we can actually store Python packages in there too. From a infrastructure side of things, we build our own AMIs, which are secure AMIs, which we then deploy out. We use Packer. I don't know if you're familiar with Packer, to build our AMIs. So that's how we build our secure AMIs that we deploy for Docker and Docker hosts and things like that. Another question: what were the non-technical challenges? I think definitely, the security, the selling the security side of this to maybe more traditionally minded people was definitely a challenge. I think we're one of the first, definitely one of the first financial services company in the UK, if not Europe, to have PCI data held in the cloud. So we're pretty bleeding edge on that, I think. That security was definitely a sort of taking people on the journey, selling the idea was definitely a non-technical challenge. I think the other one was, again, getting users engaged and seeing the benefits. It was very, they had a very kind of nice, simple environment before, because they could see every piece of data. There was no security, there was no audit, so it wasn't as easy to, or wasn't as difficult for them to work, or as difficult for them to get access to data that maybe they shouldn't have. So definitely convincing the users on the benefits of the environment was definitely a non-technical challenge. I think we've solved most of them now. We have users who the idea of scheduling, they don't have to come in every day and run their job every day, that they had to run at 10 a.m. every day or whatever. There was a lot of that going on, so we've been able to provide a platform that can give them some automation, and I think they're starting to see the actual benefits of moving on to this. Certainly performance is dramatically improved on this environment as well. Have you considered feature improvement methodology? Any critical issues that you think you'll face when upgrading any feature component? Yeah, I think it's a good question, and it's an interesting one. I think it depends on which part of the stack. I mean, if you look through if I go back to this this picture here, the further away you are from the user, so the further you are to the left, the easier it is to just to do upgrades, because you're not going to directly impact users. I'm certainly a big fan of things like feature toggles, and we have implemented feature toggles in quite a lot of areas of the stack. Certainly in the ingestion and data lake, we do a lot of things like feature toggling, so we can push the upgrade first and then it's switched off. But I'd like to do a lot more of that. On the end user space, I think utilizing Kubernetes has been a massive benefit for us, because we can actually even do a degree of like A/B testing. So we can push one image to some users and one image to another batch of users, and get feedback, or kind of drip feed users onto the environment, onto new features without impacting their day-to-day work. And we can also provide features offline without breaking the environment or bringing it down, so it doesn't impact them too much. So someone's asked what the budget for this transformation program. I don't think I don't really know, to be honest. I'm probably a bit more low level than so I haven't really been involved too much in budget conversations, but it would definitely be in the millions, I'd say. But yeah, I can't give much more detail on that, I think. So I don't think we have any more questions. I think my email has been shared out, so if you do want to reach out and get in touch, you know, please drop me an email. NewDay are hiring. We have several data engineering roles open, and obviously engineering roles across other areas. So if you are interested in joining NewDay, please have a look on our website, get in touch. We definitely, you know, we're definitely looking for good people in the data space and the more broader, you know, digital space. And obviously, I think the recording of this will be shared. So if you want to share it out with your team, that's great. I really appreciate you joining the webinar. Thank you very much. And we'll leave it there. Thank you.